Hi, my name is Daniele Antonioli. I'm an assistant professor at Eurecom, and the title of this work is BLURtooth, Exploiting Cross-Transport Key Derivation in Bluetooth Classic and Bluetooth Low Energy. This is a joint work with Nils Tippenhauer from CISPAC, Kasper Rasmussen from the University of Oxford, and Mathias from EPFL. Our work is about the security of a pervasive wireless technology called Bluetooth. And Bluetooth provides two transports, Bluetooth Classic, BT in short, for high throughput and connection-oriented wireless services, and Bluetooth Low Energy, BLE in short, for ultra-low power and connectionless wireless services. BT and BLE are specified in the Bluetooth Core Specification, a 3,000 pages document that can be freely downloaded from the internet. And this specification document, also known as the Bluetooth standard, describes, among others, the security mechanism that all BT and BLE devices have to implement, including pairing and session establishment protocols. It is important to note that one vulnerability in any of these standard mechanisms can be exploited on the whole Bluetooth ecosystem of devices. The Bluetooth standard and the research community considers BT and BLE security separately, as if BT and BLE were two non-intersecting sets separated by a clear security boundary, as we can see from the figure. For example, in the blue set on the left, we have the BT threat, including our recent work about key negotiation and impersonation attacks, codename knob and bias attacks. While in the light blue set on the right, we have BLE threats, including our recent work on key negotiation attacks. And in this work, we uncover and empirically confirm that an attacker can blur the security boundary between BT and BLE by abusing a feature in the Bluetooth standard called cross-transport key derivation, or CTKD in short. We further show that an attacker can perform impactful cross-transport attacks for Bluetooth. By cross-transport attacks, we mean threats capable of violating the security guarantees of BLE by attacking BT and vice versa. Before presenting our work in detail, we summarize our contributions as follows. We identify CTKD as a novel cross-transport attack surface for Bluetooth. We perform the first security evaluation of CTKD, uncovering 4 vulnerabilities in its specification. These vulnerabilities are critical as they affect any Bluetooth device supporting CTKD. Then we present the design and implementation of 4 new and standard-compliant attacks abusing CTKD. Our attacks enable cross-transport device impersonation, machine in the middle, and the establishment of unintended secure session. We name the attack blur attacks because they blur the security boundary between BT and BLE. We successfully evaluated the blur attacks on 16 devices from different hardware and software providers. Our affected devices employ 14 unique Bluetooth chips and span all Bluetooth versions compatible with CTKD in the market. Finally, we propose effective fixes for the blur attacks, and we discuss why the current mitigation in the Bluetooth standard is not adequate. Before describing the attacks in detail, we present our threat model. In our threat model, we consider 2 victim devices supporting BT, BLE, and CTKD. The victims want to secure their communication and start pairing over BT. Pairing is a protocol specified in the Bluetooth standard to establish long-term keys acting as the root of trust between the Bluetooth devices. The pairing initiator is called the central, and we name the central Alice, while the responder is the peripheral, and we name the peripheral Bob. Once the victim started pairing, then they negotiate the strongest security features they support, including secure connections, machine-in-the-middle protection, input-output capabilities, and CTKD support. Then the victims exchange their public keys and derive the BT pairing key using elliptic curve Diffie-Hellman. That is the blue key in the figure. Then they mutually authenticate the pairing key via Bluetooth association. For example, if both devices have I/O capabilities, they show a numeric value on their screens, and the user has to confirm this numeric value. This type of authentication protocol is called numeric comparison association and protects against machine-in-the-middle attacks. Then the victim employs cross-transport key derivation to locally derive the BLE pairing key, that is the light blue key in the figure, without sending a single BLE packet. The key is computed using a key derivation function specified in the Bluetooth standard that takes as inputs the BT pairing key and some constants. Key observation that we made in 2020 when we started this research project is that CTKD crosses the security boundary between BT and BLE, as KBLE is established by trusting what happens over BT. And we can also cross the boundary by starting pairing over BLE and running CTKD to derive KBT. We note that CTKD was introduced in 2014 with Bluetooth 4.2 as a pairing usability enhancement, but we are the first looking at its security implications. Finally, pairing over BT is completed and the victims can use KBT and KBLE to start secure sessions on BT and BLE without having to pair over BLE. Motivated by our observation that CTKD enables to cross the security boundary between BT and BLE, we defined a novel cross-transport attacker model for Bluetooth. This attacker model is not part of the Bluetooth standard and we recommend including it in future amendments of the standard. In particular, we define an attacker named Charlie that is in radio proximity with the victims and wants to abuse CTKD to attack BT from BLE and vice versa. Charlie's goals are device impersonation, machine in the middle, and the establishment of unintended sessions across transports. Since Charlie does not know KBT and KBLE, and the victims paired using the strongest security feature available, he should not be able to achieve his goals. But with the blur attacks, we demonstrate the opposite. This slide summarizes our 4 cross-transport blur attacks. By mounting central and peripheral impersonation attacks, Charlie can present as a trusted device to an arbitrary victim, both on BT and BLE, and take over the connections from the impersonated victim. As a result, Charlie can perform malicious actions as a trusted device, including reading sensitive data and sending malicious commands. Similar effects are reached by the cross-transport machine-in-the-middle attack. Instead, with the unintended session attacks, Charlie becomes a trusted anonymous device both on BT and BLE without having to break existing security bonds. This enables, among others, to anonymously access protected Bluetooth services on the victim devices. Since the attack target flaws in the Bluetooth standard, they are effective on all devices implementing CTKD, including smartphones, laptops, tablets, smartwatches, etc. Let's describe the central impersonation attack a bit more in detail. In this case, we target 2 paired devices running a secure session over BT or BLE. Since the victims support CTKD, they are always pairable over BT and BLE. And this is an issue with CTKD, as the attacker can try to pair on the transport that is currently not in use. In this example, the victims are running a secure session over BT. But what happens if Charlie tries to pair over BLE with Bob while impersonating Alice? Well, it happens that Charlie and Bob complete BLE pairing, agree on KBLE, and derive KBT via CTKD. And as a result of these actions, Charlie fools Bob into writing a malicious BT key for Alice or overwriting Alice's BT key. And Alice cannot connect back to Bob. This attack is cross-transport because Charlie affects KBT without having to send a single BT packet. And the same attack can be conducted via BT if the victims run a secure session over BLE. How can we perform the central impersonation attack in practice? So here we show the message sequence chart of the attack. Charlie sends a BLE pairing request using Alice's Bluetooth address, his public key, CTKD support, and no input-output capabilities. Bob replies with a BLE pairing response while is connected to Alice over BT. Bob and Charlie compute KBLE, derive KBT using CTKD, and store both keys, and Bob overrides Alice's key. Moreover, Charlie and Bob complete the BLE key distribution phase, where Charlie sends raw keys to Bob and steals valuable keys from Charlie. For example, by stealing the identity resolving key, IRK in figure, Charlie can track Bob even if he's using a randomized and rotating Bluetooth address. Once the attack is completed, Charlie takes over Alice over BT and BLE. An interesting thing to note about this attack is that Charlie, by negotiating no input-output capabilities, is not only downgrading the BLE pairing key to an unauthenticated pairing key, but as a side effect is also downgrading the BT pairing key that is derived over CTKD. And this cross-transport association issue is novel. Using a similar strategy, Charlie can also impersonate Bob across transports. For example, Charlie, despite impersonating a peripheral on BLE, can present to Alice over BT as a central, complete BT pairing, and take over Bob on BT and BLE. This attack not only results in the impersonation of arbitrary peripherals, but it also shows another issue with CTKD, that is about cross-transport role mismatching. And this trick about mismatching the role across transports is also novel. By combining central and peripheral impersonation attacks, Charlie can mount a cross-transport man-in-the-middle attack. Finally, as a fourth attack, Charlie can also pair on the unused transport as an anonymous device to establish unintended sessions with Alice and Bob. For example, in this figure, Alice and Bob are running a secure session over BT, and Charlie pairs over BLE with Bob as an anonymous device. And as the result of the pairing process with CTKD, he becomes a trusted devices on BT and BLE. And the attack can be conducted over BLE with Alice and also over BT with both devices if the devices are running a secure session over BLE. We successfully evaluated the Blur attacks on 16 different devices, employing 14 unique Bluetooth chips. As we can see from the table, the attacks are effective regardless of the device software and hardware details. The list of affected devices includes manufacturers such as Cypress, Dell, Google, Lenovo, Samsung, Xiaomi, Sony, Intel, Qualcomm, Cambridge Silicon Radio, and Broadcom. And moreover, from the table, we realized that the attacks are effective on all Bluetooth versions in the market compatible with CTKD. And those versions are Bluetooth 4.2, 5.0, 5.1, and 5.2. The Blur attack root causes are related to 4 issues that we identified in CTKD. And in this slide, we summarize them. The first issue is that CTKD results in devices always pairable over BT and BLE. And an attacker can exploit this issue by trying to pair on the transport that is currently unused by the victims. Second issue is that CTKD enables cross-transport key tampering. And by tampering, we mean that an attacker, by targeting one transport, can write, overwrite, and even steal security keys from the other transport. Third issue is that CTKD does not enforce association across transports, meaning that an attacker can downgrade association on one transport while the other transport expects a stronger association method. Similarly, CTKD does not enforce roles across transports, and the attacker can try to mix BT and BLE roles while pairing with the victim. In our paper, we propose 2 effective countermeasures to mitigate the Blur attacks, and we implement one of them. The first countermeasure is to disable key overwriting via CTKD unless the user consents. The user has to be notified whenever an attacker tries to overwrite the pairing key. And we implemented a proof of concept for this countermeasure for Linux, and you can see the paper for more details. Our second fix is to disable BT and or BLE pairability when not needed, and also provide a pairing UI to the user. This will allow the user to check if the device is pairable on a transport that is currently not in use, and prevent the attacker from pairing on such transport. The Bluetooth standard acknowledged our findings, and since version 5.1 includes a countermeasure that is believed to address the Blur attacks. In particular, the countermeasure is defined as follows. While performing CTKD derivation, if the key for the other transport already exists, then the devices should not overwrite that existing key with a key that is weaker in either strength, and here by strength the standard means the entropy, or man-in-the-middle protection. Such countermeasure is not effective for three main reasons. First one, it is version specific, and in particular, it does not protect Bluetooth 4.2 and 5.0 devices that are representing large portions of device in the market. Second, it does not protect against blur unintended session attacks and the blur attacks writing new pairing keys via CTKD, because this countermeasure only addresses key overwriting attacks. But even in the case where we overwrite keys, the countermeasure is not effective, as our blur attacks are not setting weaker key strength and man-in-the-middle protection level while overwriting keys. In conclusion, in this work, we uncovered that CTKD is a novel and cross-transport attack surface for Bluetooth. We isolate 4 critical vulnerabilities in its specification, and we design and implement 4 novel cross-transport attacks based on those vulnerabilities. We name the attacks blur attacks, as they blur the security boundary between BT and BLE. The attacks are standard compliant and reach impactful goals, including cross-transport impersonation and machine-in-the-middle attacks. We successfully evaluate the blur attacks on a broad set of devices, supporting all Bluetooth versions compatible with CTKD and spanning several hardware and software providers. We provided concrete fixes to the blur attacks, and we also explain why the current mitigation in the Bluetooth standard are not effective against them. And finally, we responsibly disclosed our findings with the Bluetooth SIG.